Okay, for graphing logarithms with bases that are between 0 and 1, we're going to start with a base 1/2. So log base 1/2 of x is the inverse function we are doing. And 1/2 to the negative 2 power means the reciprocal of 1/2, which is 2, to the positive 2 power. So we're actually getting 4. And then 1/2 to the negative 1 power means the reciprocal, which is 2. If I put a 0 exponent on a number, I will get 1. And if I plug 1 in, I will get 1/2. 1/2 squared will give me 1 squared over 2 squared, so 1/4. I'm going to take those points and I'm going to flip the x and the y so that we can see what the logarithm might be looking like. And I'm going to plot the points of the exponential function that we have. So I have negative 2, 4, negative 1, 2, 0, 1, 1, 1/2, and 2, 1/4. And you should be seeing the familiar exponential decay graph. And that's going to create a slightly different looking logarithm. When that is reflected over the line y equals x, it will go through the points. I'm trying to change the color of my pen. It will go through the points when x is 4, y is negative 2. When x is 2, y is negative 1. When x is 1, y is 0. 1/2, 1. And 1/4, 2. You recall that the exponential decay model has an asymptote that is effective in the positive x-axis. That means the positive y-axis will have an asymptote for its inverse function. So you should see this asymptoting up. And what you should notice is this looks identical to the logarithm graphs with the base greater than 1, except that it appears to be reflected over the x-axis. If this was log base 2, a base 2 logarithm, you can go back in your notes and see that your base 2 logarithm goes through these points. And so it's valuable to understand that if you look at the exponential function, when the base is between 0 and 1, it creates the decay instead of the growth, which the growth version is the blue exponential graph reflected over the y-axis. Well, when the logarithm has a base that is between 0 and 1, it looks like the regular log function, but reflected over the x-axis. And you can see the way that looks in a nice computer-generated function. And the domain of your exponential functions are all real numbers. That means the range of your logarithms are all real numbers. The range of your exponential functions are positive numbers only, so the domain of your logarithm function is positive real numbers only. The asymptotes, you have a horizontal asymptote of y equals 0 for the exponential blue graph, but you have a vertical asymptote of x equals 0 for the red logarithm graph. Their intercepts swap x and y, so you will notice that their intercepts are, for the exponential function, a y-intercept of 1, for the logarithm, an x-intercept of 1. So next, for your classwork, I have a generic logarithm graph. And just to point out, you cannot plug negative numbers into a logarithm, and you cannot plug 0 into a logarithm. And I want you to be familiar with the fact that you will always go through the point 1, 0 for your parent log function. And every time you plug the base in, you will get out the y value of 1. But it's a little bit challenging when the base is 1/2, 1/3. If you can find any other second point, that can be useful. And what might actually be easier to use, as long as I'm writing the bases as 1 over some number, like 3 or 1 over 4, then the reciprocal of that base, so in this case, the reciprocal would be 3, will give you a y value of -1 instead of a positive 1. So I just want to point that out, that might be an easier point to plot. The easiest points to plot are going to be where the y value of your inverse function is 0 and where the y value of your inverse function is -1. Those are going to be your easiest points to plot typically. And know that with any parent log function, the domain is positive numbers, the range, all real numbers, and understand that as x heads to positive infinity, with a logarithm base that is between 0 and 1, it will be decreasing, heading down, but it will be slowing, and it will be decreasing slower and slower, and it's heading down to a y value of -infinity. And the vertical asymptote is the same as it is for the base being greater than 1. And then I have an example for you to do, and I will point out to you where the answers are coming from. With the parent graph, if your base is a 1/3 x, first of all, regardless of the base, it's going to go through x-intercept 1. The easiest point to plot is going to be, I get an answer of -1 when I put in 1/3's reciprocal 3. But if that's difficult to remember, then you can just remember, if you are looking at the base number as an x value, you will get 1 out. And you can plot the second point there if you like. When you multiply any graph or any function by 2, that will stretch the graph's y values. So where you see a y value of 1, 0, and -1, I am showing the stretch of y value 1 goes to y value 2, and that is for this point stretching. The y value -1 goes to -1 times 2, and that would be this point, stretching its y value. But where I have a y coordinate of 0, multiplying 0 by 2 will still be 0. So there's no change in the x-intercept. From there, I have a logarithm with the same base 1/3, the same multiplication by 2 that is in part B, and we are taking that multiplied logarithm and we are shifting it. When I see plus 4 on an x, I actually want to subtract 4, so I'm moving it left 4. And when I see outside the function subtraction, I do that to the x's, so I subtract 1 to every, or sorry, to the y's, so I subtract 1 from every y, and that will move it down 1. So again, the operation to the x, you need to do that opposite operation to the x coordinates of your previous graph. The operation outside the function, you need to do that exact operation to the y values of the previous graph. And then make sure you have the correct intercepts and domain range and vertical asymptotes. The vertical asymptote will only change by shifting the x. So it will change if you see a number adding or subtracting to the actual x variable. And that concludes this classwork.